So in part 4 of the data storage, we continue to discuss other types of storage media. The first type, so we are going to focus on magnetic and optical storage. We will look at memory hierarchy and then conclude by looking at cloud storage. That is section 8, 9, and 10 of the chapter. And so as far as magnetic optical storage, these are the learning outcomes. As outlined, you should be able to describe the magnetic hard disk, discuss the tape and removable hard disks, explain the principle of magneto-optical disks, and be able to discuss the operation of CD-ROMs or the description of CD-ROMs, CDR, CDRW disks, WRM, and DVDR. So we look at first hard disks. These are used for internal mass storage in computers. They are made up of the following elements. So this would be the internal structure of the hard disk. So it will have disks, which are platters or disk platters, and then it will have a spindle where the disks are going to spin, and then it will have a number of electronics parts here, which will be controlling the actuator arm. The actuator arm will in turn have a read-write head that will be used for reading and writing on the magnetic disk itself. The case is sealed to make sure that it's dust-proof, and so that the dust doesn't get between the disks, because the spaces are very small between the disks themselves and the read head. So the disks themselves are made up of an aluminum alloy or a mixture of glass and ceramic, and then obviously coated with a magnetic material on top. The read-write head, if you zoom into it, will look like this picture on the top right, and the disk itself is random access, which means it can read any part of the disk at any point in time. You don't the way it's read, it can be read from any memory location randomly. So on the disks, there are small sections which are divided into what's called magnetic domains, and on these small magnetic domains, these are small areas which are being magnetized. So for a read operation, the magnetic field of the domain interacts with that of the read head, and that forms the voltage pulse which goes into a read head to detect whether a 0 or a 1 is being stored, or what type of information is being stored on the disk. In the write domain, what happens is the current is pushed through the read head. Sorry, in the write operation, I mean, the current is pushed through the read head, the write head, and that current induces a certain magnetic arrangement on the magnetic domain of the disk, and so that information is being written that way. So the information, we've just established that the information on the hard disk is stored on the disks themselves, and that is the magnetic domains. So the hard disk is organized in terms of tracks and sectors, as you can see in this picture. So there will be multiple tracks on the hard disks, and each track will cross within a particular sector. And this arrangement is called a format. So depending on how your hard disk is formatted, it will change the way it has formatted the tracks and the sectors. The number of disks that you get in the hard disk enclosure will vary depending on the manufacturer. However, a minimum of 2 disks is always maintained, and each address of the hard disk will address a particular track, sector, and a particular information on that magnetic domain. So the hard disk storage can be very large. In fact, it can be as big as 1 terabyte, depending on where the technology is now. The performance of the hard disk is measured using what's called access time, and the access time is made up of a combination of seek time and latency period. To understand what these terms mean, you need to first relook at the structure of the hard disk itself and how information is accessed. So remember, the information is accessed, is stored on the disks themselves, and the hard disk reads information by moving the actuator arm, which moves the read-write head. And you can tell that in order for the disk to read information on a particular track, the read-write head has to move from one position to the next position, so it has to swing in this direction. And that swinging period, that swinging motion is called a seek operation. So when a disk read-write head moves from one track to another, that movement is called a seek operation. And the average amount of time it takes for this operation, this seek operation to occur, is called seek time. It's called seek time. So and this is typically given in milliseconds. Now, once the hard disk or the read-write head is on a particular track which we are interested in, the disks themselves have to spin so that the particular sector which we are interested in is under the read-write head. And this spinning, so that this spinning motion, which will allow the disk to be positioned under the particular sector to be positioned under the read-write head, it's called the amount of time that motion takes, it's called the latency period. So the spinning motion, the average amount of time that it takes for the particular sector to spin and be positioned under the read-write head is called the latency period. And so a combination of those two periods, it's called access time. That is the time it's required to access a certain piece of information into that disk. So obviously the latency period here will depend on how fast the disk spins. So typically the disk will spin in the range of 4,000 to 15,000 revolutions per minute. So a faster disk would therefore mean a faster spinning disk would therefore mean a shorter latency period and therefore a shorter access time, which means the operation of accessing information from that disk will be better, will be shorter, which means the hard disk therefore we consider it to be a high performing hard disk. Now there is a trend of having removable hard disks. Instead of having this typical hard disk that sits in your computer, you could have a removable hard disk, or you could buy an enclosure to put in the hard disk into a portable enclosure, and this would look like this. And there is also a new trend of having removable hard disks under a different technology, which is called the solid state hard disk. This is more like this one would be built more on semiconductors as opposed to the magnetic disks themselves, and the memory in that technology can be as high as 4 terabytes. Another old type of storage is called magnetic tapes. They used to be prevalent, however these days they are not so common, but for completeness they are also included in the reference literature. So there are several types of magnetic tapes, but what we'll discuss are the two types, which are the QIC and the DTL types of magnetic tapes. So a magnetic tape would be in a form of a cassette, which contains multiple reels. These are the round things that spin the tape itself, and the tape itself is the red line that's shown here. So the data is stored on this stripe belt, in fact on this tape, which is the cray here, the cray tape that spins, and it can be read and written on by a read-write head. So the access of the magnetic tape is slower than that of a hard disk. It's not randomly accessed, it's linearly accessed, in the sense that information is accessed So at the beginning of if you want information at the end of the tape, or the whole of the tape has to be unwound in order to reach that information. So it makes it much slower. The QIC, which is the quarter-inch cartridge, looks like this. So it's the basically structure of the tape itself. It was originally designed for recording video up to 10 gigabits in capacity. It has a single write head with 2 read heads on each side. So it will have that single write head and 2 read heads on each side, and then this allows for data to be verified when it moves. So for instance, if it's moving the blue direction, as it writes the data here using the write head in between, the read head on the other side will be reading the read head will then be reading the data that has just been written to verify it. And this allows that data verification to happen on either side. So as you can see here, the tape itself would have multiple tracks, and the read write head can move from one track to the next. So it would be, in this case, it's on track number 2, it can move up to track number n. Another type is the DLT, which is the digital linear tape. In size, it looks the same, but in size it's twice as much as the QIC. It has an improved drive tape mechanism which reduces the wear of the tape. As you can imagine, the fact that the tape also brushes, it brushes across the head assembly every time you are reading or writing. It means the tape eventually wears out. So the DLT it's an improvement of the QIC in the sense that it needs to, it's designed so that it reduces that wear. The highest storage capacity of this tape is around 800 gigabytes. Another type of storage is an optical storage, and typically data is stored on a disk, and in a typical CD-ROM this would be spiral tracks which are made up of pits and lands. As you can see here, the pits would be the ditches and the lands would be top surfaces, and the data can be read from there. So maybe a pit might represent a 0, a land might represent a 1, and the way the data is read is read using a laser beam. And in this laser beam, the laser is shined on the surface of the disk, and then depending on whether it shines on the land or the pit, the reflection would be different. So the photoelectric cell here will pick up whether what is reading is a pit or land, and this becomes the information that you are reading into the disk. So there are several types of these optical storage disks. There's the CD-ROM, the CDR, read-write, DVD, and Blu-ray, for instance. The major distinguishing characteristics for each of these is that the CD-ROM, which is called the compact disk read-only memory in full, has a typical storage of around 700-800 megabytes, and it stores data on pits and lands. You would also have a read once, read many times disk worm, and the way it operates is that in order for you to write on it, you'd have to have a laser beam which bends the pits onto the disk surface so that they can later be read. There is also a CDR, which is a CD recordable, which can be written multiple times up until it's full. That is, cumulatively you can write it, and it uses, instead of burning directly onto the material, it uses an organic dye whereby the laser beam creates microscopic spots onto the disk surface that has an organic dye. There is also a CD rewritable, which uses a crystalline compound instead. And what happens is that the crystalline compound has a special behavior whereby it becomes crystalline when it's cool, and heated when it becomes crystalline when it's cool, and when it's heated it becomes amorphous. Now, because the amorphous and the crystalline areas reflect light at different rates, that is, the amorphous reflects less light, then information can be stored in the form of ones and zeros. There is also DVD-ROM, DVD being digital versatile disk. These are higher density disks, and they can store up to as much as tens of gigabytes instead of the megabyte range of the CDRs. And the reason why they are able to do this is because one of the reasons that they have small peaks, so there's a higher density there. The information is packed at a higher density, so they have small peaks and lengths. And then they also use multiple layers to store data instead of storing it in a single layer, such as in CD-ROMs. An improved version of the DVD, it's called a Blu-ray disc. And this one, the reason why it's called Blu-ray disc is because it uses a blue laser instead of the typical red laser that's used by the DVD. And it can store as much as 5 times the memory of the typical DVD. Another special type of storage, it's called the magneto-optical storage. So unlike the hard disks, which use the magnetic principle for storage, and the compact disks, which use optical instruments, the magneto-optical storage uses a combination of both magnetic and optical technologies. The disks are formatted into tracks and sectors similar to the hard disk. Now the advantage here is that the storage of the magneto-optical storage is very stable. So the way it works is that the disk requires heat. The disk requires heat to alter magnetic polarization. So this makes it extremely stable, because then it means in order for one to change the information on the disk, it needs to have both heat applied to it as well as magnetic field applied to it, so it can be easily changed. So at the heart of this technology is that there should be a laser source as well as an electromagnet for it to function. Now, if you look at the right operation of a typical magneto-optical disk, so say for example, if you look at this image here, whereby you have a disk on a substrate and the information is stored in the form of magnetic polarity of the material, and it's read by an electromagnet. So if you want to write something onto the disk, then what needs to happen first of all is that there needs to be a high powered laser to focus the energy onto the disk, and then that high powered laser will heat up the material up to a high temperature of about 2000 degrees Celsius, which is called the cool point. And when the magnetic particles are hot, their field can then be changed easily. So then the right current will be injected into electromagnet to write this information. And the similar operation will be used when you want to erase information from the disk. The read operation uses a less powerful laser beam, and the way it works is that the laser beam will shine a light onto the surface of the disk, and based on the reflection of that light, the information will be detected by a detector. And this is what's called a Kerr effect. The Kerr effect relies on the fact that polarity of a reflected laser light is changed based on the magnetic polarity of this the particle stored on the disk. So if it's down, then the laser beam will be changed. The reflected laser beam will change. If it's up, the reflected laser beam will also change accordingly. So therefore, the detector can be able to detect the information from the magneto-optical. Let's now turn our attention to the issue of memory hierarchy and discuss the several types of memory hierarchy itself, and its key elements. So computer systems have several types of memory which differ in terms of three things: the cost, performance, and capacity. By capacity, I mean size. Performance will refer to the issue of access time, the amount of time it takes to access a certain type of memory. Now, what has to happen is that um, smaller access time, memory with the smaller access time has a bigger cost, and it tends to be found at a smaller capacity within a computer system. So, in fact, so these different types of memory in a computer system needs to be arranged in the form of a hierarchy so as to lower cost and access time for the overall architecture of the memory. Some of the different types of memory includes register. Registers are located the closest. In fact, they are within the processor itself, and they keep frequently accessed data that can be used, that needs to be used by a processor from time and time. And the number of registers is quite small. They can be as small as tens or in the hundreds in terms of their numbers. The cache is the next level of memory, which is a bit bigger than registers but slower, and it provides temporary storage. There could be multiple levels of cache, level 1, level 2, and so on and so forth. Level 1 cache memory is normally found within the processor itself, whilst level 2 is outside. The next other type of memory would be main memory, which is composed of mostly RAM and some ROM, and it stores less frequently used program data. Its range could be in the ranges of megabytes to gigabytes. And then finally, we have the two biggest categories of memory. That would be the first one, the hard disk, which has very high latency compared to the other types of memory which we have talked about, because it's typical. Also, it's manual. It's mechanical in the way it operates, as you would have seen in the previous section. And the good thing about it is that it has a higher range of storage, that is in terms of gigabytes and terabytes range. And then besides that, you can have an even bigger type of memory, which is auxiliary storage. This could refer to external hard drives, or cases such as external magnetic tapes that you might have, although magnetic tapes are very old technology. So we have earlier established that within a processor, within a computer system, the memory elements are arranged in a form of a memory hierarchy. And the purpose of this hierarchy is to improve or to maximize the processing speed of the whole computer system in general, and to minimize the cost. Processing speed, how? Well, you want to have the fastest possible memory storing so that you can access it frequently. So ideally you would want to process your programs just using registers, but registers are expensive, so you put a limited number of registers, and then you augment them with cache memory, whereby you put data that you may not require as frequently. And then you do that with the main memory and hard disk, because they come at a cheaper price than the memory in the registers itself. So the biggest issue here is to make sure that you have as little latency as possible, because if you want to have a computer system that's fast, you need to maximize your processing speed. So you can only process data which arrives quickly into the processor. So if you look at latency, in terms of that, the registers themselves would have the smallest amount of latency, that is access time, of 1 to 2 nanoseconds. The cache would be relatively fast as well, with 90 nanoseconds, but main memory would slightly be slower at 90 nanoseconds. The cache is 50 nanoseconds, and then the hard disk would be the slowest component in terms of memory that you use every time, which is 200 milliseconds. And then you would have an even slower auxiliary storage that you attach from time to time. So looking at the different types of memory that you have within your hierarchy,
you can classify, or you can draw a graph here which shows the capacity of memory per type of memory. So for instance, here if you look at the orange bar graphs, they show you that the capacity increases as you move from registers to cache, memory, main memory, hard disk to auxiliary memory. So you see the capacity increases. But in terms of cost per unit, you will see that the cost of register is much higher, and then the level 1 cache is lower, level 2 cache is even lower, memory lower, and then you have the cheapest being auxiliary memory. And so this is the picture in terms of cost and capacity, which is why then you wouldn't have the luxury of having the capacity of registers as big as that of auxiliary memory, because the unit cost of a register is much higher compared to that of an auxiliary memory. And so arranging this memory into a hierarchy is an optimization. It's an optimized way of accessing your system. Now, the main reason or motivating factor for arranging this memory into a hierarchy is because general computer systems, the processing time of a computer system is limited by the memory access time or memory latency, not necessarily the speed of the processor. So the faster the memory, so memory access time acts as a bottleneck. So you want to have memory access which is as fast as possible. Two key factors are the locality and the heat rate. The two key performance factors of memory hierarchy is locality and heat rate. When you talk about locality, we talk about we are referring to the tendency in which with which a computer program accesses data from memory. So general temporal locality refers to the frequent referencing of the same data block by a program. So a data program typically would access the same data block of data frequently. So that block of data frequently, that means therefore you can have a certain limited amount of data that you can put in the fastest possible memory, so that as and when the computer program frequently accesses it's able to do so quickly. Spatial temporality, on the other hand, refers to referencing of adjacent data blocks. So typically a program also would be structured in such a way that it accesses memory data in memory of blocks that are close to each other. So this means that in fact when memory is being loaded into the hierarchy, data is being loaded into hierarchy, then it's much more efficient to load data from adjacent blocks that are adjacent to each other at a higher level, so that they can be accessed quickly. Now, there are two other concepts in terms of hit and misses that we need to consider as well in terms of assessing the efficiency of a hierarchy. So consider, for instance, here in this case, in the figure, you will see that you have a processor on top which frequently accesses memory from which frequently accesses data from the memory hierarchy. Now, on the right hand side, the processor attempts to access a request in the cache, and if that is able to access that data and finds that the data has been loaded into the cache, that data is retrieved. This transaction of requesting the data from the cache or a certain hierarchy level and finding it's called a hit. So we say the processor has got a hit. Alternatively, a processor may want to access a piece of data from the cache, and it may find that that data is not available in that cache. When it does that, then the processor is forced to look for the data from the next level, the next lower level of the hierarchy. That is, it will go to a memory, main memory, and then it finds that data to retrieve it. In this case, this process shows an example of a miss. So we say that is a miss attempt. So a miss is a failed attempt to find of the processor to read or write a block of data in a given memory level, and it forces the processor to go to a lower level. And the moment the processor does that, first of all, it has wasted time because it has attempted to read or write memory block which is not there, so it has to redo the request. Secondly, it now has to go to a level lower, which means it has to access a lower speed memory, so the access time increases. So this is not efficient. So the way in which the memory hierarchy can be assessed is through what's called a miss rate. The miss rate will simply be a percentage of memory, a percentage of misses, a percentage of misses that the processor suffers for all its memory access attempts. So that would be the miss rate. So it's a percentage. And then what's also important is the hit time. Whilst when it does really get the information from that particular level, how long does it take for it to access? So the hit time refers to the time required for the processor on average to request the information. So typically an efficient memory hierarchy would be a hierarchy whereby there is a higher hit to miss rate. So there is a higher hit rate, there is a lower hit time, and the miss rate is very low. This would result into a more efficient memory hierarchy.
Let us now turn our attention to cloud storage. So in the subsequent slides, we will look at how to describe how a cloud storage is described, be able to explain what the server is and the different types of servers that you find in cloud storage. We will look at the advantages of it in cloud storage, and we'll look at some properties of cloud storage. These are all the learning outcomes that you should achieve by completing this section. Cloud storage is basically a remote network of servers. The keywords being remote in the sense that it's distant from the user. Network inferring to the fact that there are multiple of these servers, not just one. So normally it's housed in a data center. So a data center would be this picture, would be a typical data center or server room. And each of these racks would put in multiple servers. So this would be a typical rack of servers, and each of these items here would be a server, one of the servers in the cloud storage. Sorry, excuse me. And then so this servers for cloud storage serves multiple remote users, and as you can see, there would be a user device which accesses the cloud storage over the internet, and all of these 1, 2, 3, 4, 5 would be the cloud server, the servers. There will be the control server, which has a special function to coordinate the operation of all of these other servers, and then also to manage users who are accessing the cloud storage. So typically some of the servers would tend to be organized as clusters. So you would have a control server giving a single group and another, so multiple groups or multiple clusters for redundancy, so that when one cluster has a problem, the other cluster can take over. And so this would be different types of, this would be different organizations of cloud storage. So cloud storage offers redundancy. There's in the sense that, for instance, if you see in the diagram, you would have a user storing his or her file onto the cloud storage, and then this file could be stored in multiple copies could be stored in all of the different servers. If one server faces a problem, the other servers can always give back a copy. On top of that, cloud storage offers security. Security in three forms. The first form of security will be encryption. That is, the information communicated between the user and the controller is secured so that nobody can eavesdrop on the information. There will be authentication to ensure that only people who have the right to access the cloud storage do or are able to access the cloud storage, and then there will be authorization to ensure that there's different levels of access onto files which are on the cloud storage. For instance, you wouldn't want a user who's not mandated to be able to edit a file to edit it. Other users, you just want them to view and read the file, whilst others will be able to edit these files. Some of the key advantages of cloud storage are the fact that you can store and retrieve data from any physical location with internet access. Another advantage for the user is that it's free, it's maintenance free, in the sense that the user need not maintain the components of the storage that he or she is using. And then the other advantage being there are no logistical challenges involved. You don't need to carry the storage around as you move as a user, in the sense that you don't need to carry the server with you if you're going to need information from a different location. So the important characteristics of cloud storage are latency, that is the time taken between the user's request and the delivery of the data that the user has requested. The bandwidth simply refers to, it simply has an implication of latency, in the sense that the wider the bandwidth of the cloud storage, the lower the latency, which is desirable actually. And then you have scalability, which means the ability to handle increasing amounts of data. So for a cloud storage, you can either scale up, which means it on a server as and when demand increases for the storage, the maintainer of the cloud storage can increase memory or can increase the processing hardware in order to keep or to improve latency. Or alternatively, it can be scaled out, so cloud storage, which means more servers could be added to the cluster of servers as and when required. And another property is elasticity, which simply means that cloud storage is able to vary with increasing or decreasing amount of data, so variations of data. Even when less cloud storage is required, the cloud storage provider can scale down, and from the user's perspective, they can use less. So it's elastic in that sense. It can go both up and down. And the other important property is multi-tenancy, which refers to the ability of the cloud storage to be used by multiple users. At this point, you have reached the end of the chapter. Consider the problems related to the nodes that have been presented. That is the problems relating to sections 1 to 10 of chapter 11.